What I'm going to talk about today is the fourth dimension of mineral systems, which is basically the time dimension. And I think this is quite an important aspect of mineral systems, but also I think time is one of those dimensions and one of those things that's really geology's great gift to our scientific understanding, right? That concept of deep time that boggles the mind, 4.5 billion years of Earth history. Yet a mineral system itself might only be formed within a brief episode within that huge history. So I guess when I think about mineral systems, we've got the beautiful concept of basically an architecture, a fluid, and a structure to move that fluid within, moving material from a fertile place. So the mineral systems concept. I would throw a slightly different wrinkle into that and point out that time is also important. So what you're seeing here basically is this kind of concept of a fluid flow event with this punctuated geodynamic trigger leading to a short interval of mineralization, moving widely distributed material along a structure. Interestingly, it can be fluids from the surface or it can be mantle-derived fluids from the bottom up. And we'll talk about this and being able to track the direction of these fluids. We want a punctuated event because a punctuated event is what concentrates metals. If we have a long-lived event, what tends to happen is we get a distributed and dispersed halo. And then obviously we need it within a preservation place that we can actually reach it and extract it. So this diagram is basically trying to say that with architecture and fertility, we also need to think about time. If we look at this in a slightly different sort of concept here, we can basically think of space as the bottom here, but time as this vertical axis, and where fertility, plumbing, and preservation all come together along with time, we might be in the ore window. So I think it's reasonable to say time helps turn geology from descriptive into a bit more of a predictive system. So we're helping to reduce exploration risk by adding this time aspect into our mineral system. So what do I mean by time? So time is not just, what we think about on a watch. It's not just when something happens. That's one aspect, but it's also the duration, how long something happens. That provides another signature that's important. So we've got when it happens, a date. We've got a duration, which tells us something about the process. Different geological processes have different durations of time, so that helps understand the actual process itself. Not only that, we also have the frequency. So how often are these things happening in time? Is it a one-off event, or is it an event that happens multiple periods of time? So frequency itself can be a useful descriptor. So all these things together can give us a signature for specific types of mineral system. They give us a recipe in terms of time, duration, and frequency that can be consistent for different types of ore deposit. So I'd like to structure this talk is say something a little bit about how we tell time in the geological record, how we date materials, or in some cases, how we can't date materials. But I'll show that's all right. When we can't date something, there's actually other information we get at the same time then. That brings me on to the idea of when geochronology doesn't work, and that's when we're looking at source signatures. And then we'll come right at the end to this idea about the repetition frequency of events, the periodicity of events, so how often events are happening in time, and what that can be used for. So that's the kind of menu for today. I do need to say lots of the ideas within this have basically come out of work within the research group, the Timescales and Mineral Systems group at Kirkland University, which is about 10 people now. So this is a bit of a team effort. So just a bit of 101. So when we think about a rock and we think about isotopes within that, we can think about the decay of a parent isotope to a daughter, and that's controlled by a decay rate. And if we know the decay rate, we can measure the amount of parent, we can measure the amount of daughter. Hey, we've got an inbuilt clock. Zircon, the geologist's best friend, is really good at that because it likes to take a lot of parent in at the start of its crystallization, but it hates its daughter product, i.e. lead. So that means over time, we've got a really great clock. That's awesome. Okay, so we get a big smiley face for that. We've got a clock in our rock. But what happens, something like feldspar? Feldspar in the uranium lead system, feldspar hates uranium, but it loves lead. So it will capture a lead signature. That lead signature won't change over time, but that lead signature is actually really useful because it then becomes this signature or fingerprint of the source fluid that feldspar grew from. So this mineral, great as a clock, useless as a source fluid tracer. This mineral in the uranium lead system, useless as a clog, but really good as a source fluid tracer. So that's what I mean. When one system fails, using it one way, we can flick to the other way of using it, and it still can give us useful geological information. A nice way, actually, I think, about thinking about source information or source fluid information is thinking the idea of a surname. So my surname is Kirkland. You can tell I'm from like Scotland with that surname. Just like a lead isotope signature in our feldspar grain tells us where it has come from. It doesn't necessarily tell us about its direct age. Okay, there's some other things I like to think about and put things on a scale. This is the idea of ranging from a source tracer, an isotope tracer, all the way through to a geochronometer. So we've kind of already talked about this. You know, down at the source tracing end, we can think of apatite. It doesn't like rubidium, so it's mainly strontium. That strontium source signature can tell us, is it a mantle-derived fluid or a crustal fluid forming our apatite? All the way through to a really good chronometer at the far end. But we have systems in the middle that give us age information as well as giving us source fluid information. Looking at this scale in a different way, it's not just an age. What does an age mean? An age can mean when a crystal grows. That's useful. We can tell when an ore deposit forms. Or it can also tell us about a time temperature point, and that's the idea of closure temperature. So basically, above the closure temperature, we're losing the daughter product from the system. But as we go beneath that temperature, we start to retain it. And because we're now able to work with a vast array of different minerals and different isotope systems, we can track through the crustal column a rock using different minerals. So we can tell when that rock crystallized. We can tell that when that rock moved through, you know, about 500 to 600 degrees C, uranium, lead, and titanite would help us there. 300 to 400 degrees C, if we looked at the rubidium, strontium, muscovite in that mineral, it would tell us about that event. If we wanted to know about later landscape evolution and uplift events, we might look at fission track or uranium, thorium, helium, and apatite. So we're now able to combine these different chronometers together to literally track a parcel of rock as it moves through the crustal column. That gives us a much more complete and holistic understanding about the mineral system, but also the landscape evolution that our mineral system is sitting within. Okay. So what I'm going to do now is go through some case studies that I think are quite informative, hopefully a bit of fun as well. Just before I get there, I just want to point out that a lot of the work that we do now is petrographically constrained. So when I was doing my PhD quite a while ago now, we took a rock, we crushed it up. We spent ages in the lab passing it through column chemistry, passing loads of acid through it, and you got a bulk result. That's not really what we do very much anymore. What we do now is much more petrographically constrained. We worked in thin sections. We use laser beams and ion beams to directly target material that has got petrographic context retained. So here's an example of a mineralized vein. This is from the Nifty deposit. You can see monazite here, and you can see its association with sulfide materials is kind of important in making an interpretation about what the geochronology means for our mineral system. If I crushed this rock up and dated it on a whole, on an aggregate, I would get an age, but I would be struggling to understand what that age meant for the mineral system. It's not only on the thin section scale that we can see complexity. Here's some zircon from carbonatites in the Arunta region. These are beautiful pictures. So you can see primary oscillatory zoning, perhaps telling us about a primary magmatic process. But we can also see these crystals have been in a very reactive fluid. You can see these invade regions, these dissolution reprecipitation textures. So placing our spots, our analytical spots in different position, even though we're looking at the same isotope and the same mineral, can bring a lot of extra information. So that's a long way of saying most of the work we do now is in these petrographically constrained techniques, where we first create maps of our samples, and then it's really a case of what instrument do we want to use, what spatial resolution do we need. Do we want to dig a reasonable size hole with a laser beam, or do we want to fire an ion beam at stuff using a smaller spatial scale? And we're blessed at Kirkland to have a huge amount of different instruments and choice in that area. All right, so what I want to tell you about now is some in situ rubidium strontium geochronology. And the reason I find this cool is that it's a relatively new technique. The traditional way of doing this was column chemistry, losing all that petrographic context. But now we can, literally shoot thin sections. So just a polished thin section is perfect for us. So it's a technique that's based on the decay of rubidium to strontium. So it's an isochron technique. An isochron technique basically means as time progresses, the slope will change of this regression. So at time 0, it'll be a flat line. As time progresses, it migrates upwards. So the slope gives us age. But the also cool thing about this is that point there, that intercept on that axis, gives us the initial strontium. The initial strontium is basically a signature of the fluid that mineral grew from. So it's giving us a fingerprint of the fluid. We can tell if these minerals are growing from a crustally derived fluid, a mantally derived fluid, hydrothermal fluids. So we're getting age and source fluid information at the same time. But, this technique is actually relatively challenging. It's a beta decay system. So I'll go into a little bit of detail about why it's challenging and why we can only do it now. So what we need is called a triple quad. Now, it's called a triple quadrupole because there's 3 quadrupole elements in that. Why is there 3 quadrupole elements? Well, there's 3 quadrupole elements because we're trying to do something quite challenging. What we're trying to measure is rubidium and strontium. The problem is our rubidium at mass 87 is going to interfere with our product 87 strontium as well. So they're sitting in the same place. They're also not very high mass abundance. So we need a very sensitive instrument, but we also need an instrument that is able to remove the interferences. So what we're going to do, and basically you can see here, we're going to pass our signal into a reaction cell and let that reaction cell do our column chemistry for us. So it's essentially doing chromatography for us. The instrument is doing our chromatography in the gas. It's reacting in this gas, removing all these other products, so we get a signal that we're actually interested in measuring. So if you look here, you can see we've basically got our strontium sitting here. He's surrounded by his mates, which I don't really like because that's going to give me a mixed signal. It's going to give me a mixed isotopic mass signal. It's got all these lads adding up onto that signal peak. What I really want is a clean signal so I get the true daughter product. And that's basically what this reaction cell is doing for us. What is a quadrupole? Well, it basically shows you here. It's 4 bars that are creating a magnetic field that then cause the beam to pass in a helical corkscrew direction down it. If we change the voltage, creating a different field on this, we can basically collide out and move out of the signal pathway material that we're not interested in. So we're letting through just the signal we're interested in. So this part of the instrument, this reaction cell, is relatively new and what allows us to do what is really quite challenging chemistry in the instrument itself rather than through chromatography. So what we're going to do is we're going to go and look at we're going to go off to Tropicana and go to look at some shear zone related gold actually, no, we're not. We're not going to Tropicana first. What we're going to do is we're actually going to go to the Zerleke shear zone, close to the Ida fault, and we're going to look at that. So some original work by Cyro nicely was able to separate 4 different mineral associations and alteration associations. And they were able to place it in relative chronology just based on the different petrographic relationships. What we did is we looked at the biotite within each of these different petrographic settings, and we were able to calculate isochrons for those. So that's, where the steepness of the slope is telling us an age, but we're also getting source fluid information from this part of the diagram. I was really pleased to see that the petrology in terms of the relative order of this alteration assemblage was actually the same order that we got from the absolute dating of these different biotite phases. So what we started out with is an early biotite phase about 2.5 billion years ago, then an early stage about 2.7, a main stage about 2.6, and then a later stage about 2.5. The mid stage, which is associated with the ore deposit at about 2.650, we were able to constrain the temperature of this as well by looking at the chemistry of those grains at the same time. So this really helped provide absolute numbers into a petrographically constrained sequence that already existed. It's not just isotopes. As I said, we could look at the simultaneously to get to calculating an age. We could also measure the titanium content of those biotites. Titanium and biotite gives us a thermometer. So we could look at the temperature of those fluids that are growing the biotite at the same time. And you can see that the mineralization here is just post-peak temperature. This fits into a kind of a crack seal model of this ore deposit where you're basically repeatedly passing fluids into the same shear zone system. That shear zone system is locking up, crystallizing, but then you're having a new phase of fluids passing along that same zone of structural weakness and forming on the margins of that same deposit. And that happens multiple times. So it helps us understand the process. Okay, now we're going to Tropicana, right? Off to Tropicana. So Tropicana is basically in the Albany-Fraser origin on the margin of the Yilgarn Craton. It's a high-grade granulite facies gold deposit, but we were interested in knowing something about its overprinting history because we know there's more than one gold phase there. So we're going to use rubidium strontium there. So what we could see from petrographic images, you can see there's 2 different generations of biotite here. You can see there's this nice kind of clean biotite 1, and then you can see there's this more ratty, overgrown biotite as well. This is a 100 micron scale bar. These are the size of the laser spots. They're about 60 microns or so. Oh, I should say, if people get really interested in stuff, they can take a shot of the QR code and you'll go and hear directly from the authors. So what we're going to do is we're going to use these minerals to look at their rubidium strontium isotope systematics to help us give an age on the system here. What you can see is there's different generations of biotite, and that's reflected also in the isochron. We have this older isochron at about 2.5 billion years, which is telling us something about the early phase of growth. That is also related to a mineralization stage, but what we can also see is there is this alteration. So you can see the isochron is falling towards this younger line, and the texturally young biotite is sitting on this other isochron. So it's telling us about an alteration event, and this is a kind of a widely known age. This 1.2 GA age is a widely known Albany-Fraser stage 2, so it's a widely known age of overprinting in the region. So we can now fit this into a bit of a broader context, so we can see that there is an early phase of mineralization associated with high-grade metamorphism, but there is also a later stage of mobility And that later stage of mobility is coeval, or at the same time as we're getting other mafic rocks and granites placed into the wider orogenic system. So this is a time-space diagram. So on this side, we've got the Yilgarn Craton. As we go further outboard here to the east, Tropicana Zone, Burren-up Zone, Fraser Zone, Normal-up Zone, these are eastward directed zones. Ages of sedimentation are here. So we've got early gold formation, another gold formation event, and then this late gold formation event as well, or remobilization and recrystallization, because it is essentially remobilizing this earlier Archean gold system. We can go a little bit further with that. What we're going to do now is move down to what's known as the Harris Lake Shear Zone, which is a shear zone that sits further to the east. And we'll just start off and look at some drill core. That drill core has got quite a lot of zircons in it, geologist's best friend. Those zircons, unsurprisingly, give us a detrital zircon signature. So that's telling us a fingerprint about that source sediment. Okay, so we know something about the source sediment, but we also get this 1.2H. So there's a metamorphic overgrowth on those grains. What's interesting about that metamorphic overgrowth is that if we look at the chemistry of these zircons, you can see there's these two distinct patterns. So this is the rare earths, heavy rare earths on this side, on the left-hand side, the lights. You can see there's this depression, this flattening of the metamorphic zircon, which is in green. You see the way it's flat here, and then these detrital grains in red are on this steeper profile. So that tells us that these zircon are growing along with garnet. Okay, the garnet is going, hey, give me all your heavy rare earths. I'm taking that away. You're not going to have it. So it changes the signature of our zircon grains. So that's great. Our zircon is telling us about the earlier history. But what we want to know about is a bit more about the mineralization system itself. So basically did a case study, or a natural laboratory study, if you like, of an altered system, an altered gold mineralized shear zone. So the red bars here are the gold in ppm. This is the stratigraphy, so it's a sequence of metasediments, the parenesis. We looked at the zircon, which you've just heard about, but now we're going to look at the rutile. 3 different samples going from away from the ore zone into the ore zone itself in the shear zone. So what's kind of interesting is that we can see the rutile is a later phase. It's overgrowing our zircon. The rutile is associated with a pyrite and gold, so it's more related to the ore zone system. So the timing of this is probably going to be more related to the gold system itself that we're seeing in this shear zone. We can also see an age, or get an age from this. So these are known as Concordia diagrams. Geologists or geochronologists really like data where it's all sitting on this blue line, because you can make a more straightforward interpretation. But for rutile, what we find is there's some common lead. Remember, that's lead that's not produced in the system as it decays. It's what's captured from the primary fluid that it grew from. But there's also a radiogenic component. The radiogenic component is giving us an age. It's about 1.2 GA. The line here is a mixing line, so we can just draw a line through that. So we've got an age of our rutile. That's great. Okay, so we've got an age of our rutile. We know it's associated with the gold. What else can we see? Well, with our 3 samples, there's this really nice progression. So the progression basically goes on this ternary diagram from titanium, tungsten, iron, chromium, vanadium. We can see that the unmineralized samples are sitting in here. The mineralized samples are sitting further away towards each of these axes. So basically what you see is the increase in all those elements. So we can use this as a kind of a tracking tool, and it's much more widespread than the actual shear zone itself. So it helps us vector towards the deposit. Close to the deposit, you're getting these widely distributed signals. As we progress away from the deposit, you basically migrate inwards towards a more consistent signal. So the chemistry of the rutile itself is a really useful vectoring tool in this shear zone. And it also tells us that stage 2 mobilization of gold is quite widespread along the Albany-Fraser origin, which is pretty important. Okay, that's telling the time. What about telling the source? So you remember when I said at the start that, geochronology is about time. When that doesn't work, we can maybe tell where something comes from. So it's like this isotopic fingerprint, this indelible signature. It's even more powerful than that because different isotope systems tell us about different positions within the crustal column. So we can look at the lutetium hafnium or samarium neodymium system. That typically tells us about when material is taken out of the mantle, because the fractionation system that sets that up is a fractionation between samarium and neodymium, or a fractionation between lutetium and hafnium. More mafic material prefers to retain the parent in that system, so over time it produces more radioactive product. So these sorts of fractionation processes are deep fractionation processes in our planet. The uranium-lead system and the rubidium-strontium system are telling us about a fractionation process that's typically involved with granite production, where uranium and thorium are being concentrated in our granite production factory. That's usually in about this kind of intermediate depth. We can also look at oxygen isotopes or silicon isotopes that tell us something about the interaction with the hydrosphere. So we can combine these different systems that fractionate in different places that don't change over time, because we're only looking at a product. We're not looking at the change in that over time. And we can fingerprint where material is coming from. Is it coming from deep in the mantle? Is it related to thickening of the crustal column, or is it related to interaction with the hydrosphere? I'll show you how this kind of works. So the survey has been doing this for quite a long time. We can, this is quite a well defined map. We can certainly fill this in with more samples, but you can see it resolves very nicely the Yilgarn craton, the Pilbara craton, but it resolves this, the margins of those cratons with new juvenile input that are younger crust. The importance of this is it's essentially time-resolved geophysics, because for each point, we've got a piece of time information as well as a piece of source information. So what you're looking at there is the Eastern Yilgarn and Albany Fraser, and what we're looking at is the input of juvenile material into the crust. Juvenile material is bringing mantle-derived material into the crust, and we know that carries metals. I can demonstrate this in a slightly different way. This is an evolution diagram, so time is on this axis. On the vertical axis is epsilon hafnium, so just treat that as where we're going more towards the top is more mantle input, more juvenile input. Going towards the bottom is more crustal input, or reworking of that crust. And you can see there's basically this stair-stepping pattern where we've got magmas coming out of the craton itself that are being reworked with a new magma. So we're reworking the same material. And then we're suddenly starting to add new juvenile material about 1.6 billion years ago. And that material, you can see, has got a more juvenile signal. But it's not just juvenile addition. There is also, at the same time, reworking of that old crust. You can see it lies along these similar evolution lines. So it's sitting down here as well as up here. So that's the thing about crust production. Crust production typically isn't just a single process. It's not just juvenile input. It's juvenile input plus reworking of the existing crust that's there. We can go even further with that. So what we can do is, at the same time as looking at our hafnium isotopes that are telling us about this pattern, we can look at oxygen. Oxygen, remember, tells us about how deep we are in the crust, right? Where we're near in the shallow crust, we're interacting with the hydrosphere. When we're interacting with the hydrosphere, we get a different oxygen isotope signal. So in blue, what you're looking at is material that has an oxygen isotope signal broadly within the range of mantle. In gray, what you're looking at are analyses that have interacted with the hydrosphere. And what that allows us to do is separate material that's been reworked from material that is true new additions. Doing that, you can basically get these two different histograms that pull this data apart, and they're really informative. So what you can see is that you can see that there is new mantle addition. That new mantle addition, like I said, seems to be peaking at just after 2GA, whereas the earlier magmatism, although it might be even more voluminous, tends to be reworking. And that's important for understanding the processes of when metals come into the crust. We can look at this spatially. So if we map this data up and look at material that's 1.8 billion years old, so this is material before these rocks actually formed. These rocks are in the Fraser zone. We know they're 1.3 billion years old. So that part of the crust already at 1.8 billion years old was already preconditioned to have new juvenile input. It's probably no coincidence. It's where the greenstone belts cut the margin of the craton. So we can see this crustal preconditioning before it actually happens. So we can make predictions about where ore systems are likely to sit even before those ore systems form themselves. We can go further than that. We can now look at lead isotopes. I'll do this quite quickly. What we can look at, remember I said our feldspar doesn't like uranium, but it loves lead. So over time, it's not going to change. So we don't have a clock, but we've got a source signature. So what that means is if we're measuring lead isotopes 206, 204, 207, 204, over time we're predicting the crust to evolve along this red line. If there's more uranium in that system, it'll evolve along the black line. So they evolve along these curved trajectories depending on the amount of uranium. More uranium, they're going to go higher on that diagram. Less uranium, they're going to go lower on that diagram. So if we have two samples, we have a more mafic sample in yellow and a more felsic sample in red, and they're the same age. They define a line. That line gives us the age, but not only that, it tells us that this sample has more of a crustal signature. This sample has more of a mantle signature. So let's go and have a look at that spatially. So what we can see is if we look at this spatially over the Gawler craton, we can basically map out these regions of higher uranium. And what they're actually telling us about is thicker bits of the crustal column. They're telling us about more fractionated crust that has developed thicker parts of the crust. If I then put on copper deposits, you can see they're basically on this gradient. And that's the gradient between thicker crust and thinner crust. If we go and look at this in the Yilgarn craton, and we do the same sort of thing, you can see that we're resolving similar sorts of images to these other isotope maps, these neodymium maps that have been widely used. You know, you can resolve the Ida fault here. You can resolve this younger part of the eastern goldfields. You can resolve this Q rift zone. But if we look at the lead isotope signatures, which are telling us something about a higher level in the crustal column, you can see they resolve a broadly similar pattern, but there's slight differences. You might say there's maybe more similarity with the mantle S wave velocity. If we look at this statistically, what we can do is we can look at those isotope parameters. You don't need to really worry what they are. They're basically telling us about uranium, which is mu, kappa, which is telling us about the relationship with thorium, and then omega, which is telling us about the relationship between the two of them. We can place some statistics. So we can basically use what's known as the Shannon-Weaver diversity index, and that's what people use to look at ponds. There are loads of different tadpoles in the pond, very diverse pond, lots of different animals in that pond, great. What we can do is we can use the same statistics and help us understand, are we looking at a variety of different sources in our metal fluids or a simple fluid in our metal sources? And what I want you to see is that in our gold ores, in both the Eastern Goldfield superterrane and the UME superterrane, you can see they're much more diverse in terms of these isotope signatures. That tells us that the fluids are more diverse. And it's really, you know, this is statistically significant. We can see they're much more varied in terms of those signals. So why are they more varied? Okay, so this is where I put up, oh my goodness, not another lead isotope diagram. But I'll try and break this down because if you get it, I think it's quite cool. This diagram is showing 206, 204 against 208, 204. So this axis is controlled by thorium, so the amount of thorium in the source. And time is controlling the x-axis here. So time is going to move things along this axis. And kappa, thorium content, is going to move us up and down. So you can see this kind of triangle. These are samples from across the Yilgarn, including pretty famous gold deposits. You can see this kind of triangle. And I think what that's saying to us is we need two sources. We need a source that is coming from old crust, but then we need a lower source that is being thorium depleted. In other words, it's had a high-grade metamorphic event in its prehistory that has removed thorium. So we can say something not only about the diversity of those fluids, we can actually maybe track where those fluids are coming from. And that helps us build up a model of these gold fluids probably coming from deep, coming from a source that has had a high-grade metamorphic event in its prehistory, but then transiting upwards and interacting with old fertile upper crust where more fluids are being released and mixing with that other signature. All right, I'm coming to the last part of my talk. So this is where we talk about the frequency of events. So remember, we've talked about time, we've talked about where material come from. Now we're going to talk about the frequency, which is how often events happen. So this was kind of picked up in the 1950s that there was a pulse of events every 250 million years. This idea of mountain building, glaciation, basin formation linked into cycles. But we know about cycles from a whole range of different scales, right? We know about cycles with Milankovitch cycles, about our orbit around the sun, but there's cycles within our planet itself. One of the interesting things about the fact that there's cycles within geology, it actually has an implication for us. The further back into time we go, the harder it is probably to resolve these cycles. And the reason for that is that if we have a short period process, which I'm representing by this up and down, and we've got information from a specific temporal window, we might be able to resolve that process, that characteristic signature of an event. Let's say it's, I don't know, garnet formation during orogenesis. Let's say it's happening every 100 million years. Sure, we can resolve that event because it's happened frequently. But if it's a process that has a long repetition frequency, that's really hard to resolve if we've only got a limited temporal window. What that means is the further back into Earth history we go, we need to look over a bigger spatial scale because time and space are connected. So if we've got a bigger spatial scale, we can actually resolve those processes that potentially have larger repetition frequencies. Kind of extending on this idea, Dave Houston at DA, really nice paper I like, is this idea of the convergent margin metallogenic cycle, where he basically has recognized this repetition of BHMS, porphyry copper, orogenic gold, pegmatite, rare earth metals, and they repeat in that frequency, they repeat in that order over the supercontinental cycle. That's the periodic breakup and aggregation of continents. So that periodic breakup and reaggregation of continents is associated with metal production on a similar sort of time frame and in a sequential order. What is interesting is that the frequency of this seems to be coming faster, but not only that, the system seems to be becoming more complex. So at the start, you might have only had one metal system, whereas with modern style subduction, we have multiple overlapping metal systems. So can we extract even more information from this? And this is where I talk about a little bit of easy maths, but I think it's a pretty cool idea. And this is the conversion of information that's in the time domain into the frequency domain. So what do I mean about that? So we've got a signal here. This signal will be made up of individual components that are repeating. And if we can break this signal down into its repeating components, we can perhaps say something about the processes that are going together to make this signal. So this is the idea of the Fourier transform. So Fourier transform is basically like taking a cake and unmixing a cake. So it's a bit of mathematical wizardry, but it's one of the probably most important bits of maths there is. It's used to encode a lot of information in the computer sciences. It's how we basically make images in biomedical sciences. It's how we encode information that we pass via radio waves. So how do we unscramble a cake? Well, we can unscramble a cake to get its individual components by passing it through this kind of recipe. The recipe basically says, take a waveform and describe that waveform by producing it with a circle. So that circle will have an amplitude, it will have a starting phase, and it will have a frequency. And I can show you how this works quite easily here. So we've got a simple sinusoid here, this simple up and down. It's described by this rotating circle that has its own frequency and size. Let's make this into a more complex signal. Let's add another frequency component. We can do that by adding this other circle, which is rotating around. We can make it even more complex by the blue, and even more complex with the red. The point is I can describe any time series or any frequency with this technique that will deconvolve it into its individual components. So if we do this, let's just take pegmatites, for example. So this is let's start here in this diagram. Our pegmatites, our age of pegmatites on this histogram. So this is time in billions of years, and we can see they repeat in frequency. We can convert it using the Fourier transform to its frequency component. So that's how often things are repeating. So this is what the blue line is saying. This is a statistical significance level. So when this blue line gets above the orange line, that tells me about a significant frequency. And it tells me that there's a significant frequency of about 800 million years. Now that's interesting. 800 million years is the same amount of time that the supercontinent cycle takes. Okay, so in our ore data of pegmatite-based ores, we're seeing a supercontinental signal of 800 million years. We can go further than that. So just stick with me here. So what we can do is we can take the sampling band in this orange box, and we can pass that through our data set. So by doing that, I can now get the frequency component through time. In other words, on this diagram, you can basically have time on this axis and the period, in other words, the frequency, when things are repeating. Red is when there is a strong signal. So if I increase the size of that window, I can create this axis on the diagram. The curved margin is basically saying that for a very long period, i.e. the whole length of Earth's history, I've got poor confidence on this side of the diagram, but I have good confidence on the inside area. So you can see as I get to higher frequencies, I have got a longer period of time I can say something about, and that makes sense, right? If I take a window in here and pass it along, I've got more ability to create data than taking one big, large window. So just read things inside this kind of triangular shape. And what I want you to see is, you see this red going from top here to bottom there? That's kind of important, right? So it starts out at, it's averaged around 800 MA, which is basically what we can see here. But it, in detail, seems to be going down, starting high and going down low. So that tells me that our pegmatite repetition frequency through Earth history is decreasing in time. So it started out about 1 billion years. Every billion years, we were getting a pegmatite style deposit, and now it's ended up at about every 600 million years. And you can do this for gold deposits, and you can do this for other deposits as well, and it roughly comes out the same. And it's telling us about the relationship between ore systems and the supercontinental cycle. So why is that the case? It's a bit counterintuitive, right? We're on a planet that's cooling down. So if we're on a planet that's cooling down, why are our ore systems speeding up in terms of their repetition, their frequency? Why are they becoming more frequent? So I think it's probably to do with this idea that our slab pool is becoming stronger. So we're getting colder slabs, stronger coupling. So subduction is therefore becoming more efficient. Subduction is becoming more efficient, therefore we're speeding up the supercontinent cycle. So that's been quite a big question in earth science for quite a while. What is the frequency of the supercontinental cycle? People have made estimates before, and I think it's cool that we can make an estimate out of the timing of mineral deposits. But not only that, we can show that that frequency of the supercontinental cycle did not stay the same, it speeded up. Last slide, we can go a little bit further. What we can do is we can look at we've got a time series, so that's the frequency of events. And we can pass the two different time series against each other. So let's say we've got our supercontinental cycle in black and another time series, let's say our ore deposit time series. So if we pass these two time series against each other, we can look at their correlation. Now that's pretty cool, because what I can do now is I can say, is there a correlation between an isotope signature and some other process? So what I want to look at here is our mantle input. I can get at that by looking at our neodymium system. So I'm looking at mantle input versus deposit counts. Deposit counts for the HMS, deposit counts for orogenic gold, and deposit counts for pegmatites. And what I want you to see is they line up. So the time series of these systems is perfectly lined up. That's nice. So what we're now demonstrating is that this spatial relationship between neodymium isotopes and mineral systems is also a temporal relationship. It applies through time. Where there is more mantle input, we're getting more VMHMS, orogenic gold, and pegmatites. We can go one stage further and look at, remember I was talking about oxygen isotopes, so this is the diversity of oxygen isotopes. So this is telling us about interaction with the hydrosphere. And you can see there appears to be this offset between pegmatite deposit count and when we're getting most variety or most interaction with the hydrosphere. So what's that? And why is it a 300 million year offset? Well, that's kind of interesting, because 300 million years is about the length of time a supercontinent exists. So what we're seeing is supercontinents form, they exist, and then at their end of their lifespan is when we start to generate more pegmatite deposits, and that's why we're seeing this 300 million year frequency. So it's telling us about this sequential pattern. So final slide. I think, we're happy with the mineral systems concept. It tells us to look for structures. It tells us to look for fluids, moving materials on those structures. I think the added wrinkle into that is it's not only where, it's when. We need these things to come together in time. So adding time into our mineral systems concept, I think, is important. So maybe don't just ask, where's the right geology? Where's fertile geology? That's important, but also maybe ask, when was this crust mineralized as well? Thank you.